Okay, so here we are with lesson 6 practice work, and it seems to be a little bit ambiguous in the questions, but the answers are pretty straightforward once you know what they're asking. So it says that you have these two triangles, RHC and RHC prime, and it says explain what method can be used if all the angles have the same measure of the two triangles. Well, what measures of what? What are they asking? Well, all they're saying is if I have, this grid paper or anything like that, and if I have, two of the same triangles, RHC right here, RHC prime right here, what method could I use to join them together or whatever? Well, because they're obvious reflections, right, across this axis. It looks like it's like the y-axis. Well, in order to join them together, explain what measures can be used to determine if each angle has the same measure, right? You can take this, right, and you could fold them across each other, and you could show that each angle has the same measure, right? So if you do that, that's what they're really asking for is you could fold the grid paper at the dotted line and line up the angles to match. So that's my answer for those ones. You could line up the corresponding angles. To match. I'm gonna make that. I have a pen to erase for a reason, I guess. So the corresponding angles to match. Right, so the next question is, or reads, explain what method can be used to determine each side has the same length. And, well, the answer to that is effectively the same thing. You can fold the paper over the dotted line or the reflected line and match the sides. You can fold the grid paper over the dotted line and match the corresponding line segments. Okay, and then here it's next one is reading. Explain why the transformation shown on the grid can be classified as isometric or isometry. And if you can remember from Unit 1, well, it's because that both the angle measures, both the angle measures of the angles, the measures of the angles and line segments which make up the triangle do not change. preserved. Okay, so that's the answer to that one. Okay, next is we have two line segments, HN and HN prime, and then it says to show a mapping of them. Okay, well this is a really simple, super simple. It's gonna go. I'm gonna go down and over, down 2 and over 3, down 2 and over 3. Boy, that was tough. Okay, C orange mapping lines. Okay, describe the transformation that was applied. Well, I went, we'll just do it with an algebraic expression, right? But x comma y yields, jumped to my delta too quick, yields x, and then my x was plus 3, my delta x was plus 3, comma, my y was minus 2. That was pretty easy. Oh, wait a minute. I went backwards. I went this way. I went that way. So I am opposite. Opposite. So like that. Opposite. Okay, now I'm going to complete the statement. H and N can be mapped to H and prime N. So each point, so if there's like how many points are on a line segment, well, there are an infinite amount of points on a line segment because points have no dimension. They're dimensionless, so there are an infinite amount of points on the line segment. So each point on HN can be mapped to the corresponding points on H prime N prime. So every single point on here can be mapped to its corresponding point on here. So that was that. Moving along. Okay, break out some more patty paper. All right. Maybe you get a fresh piece. Got a fresh piece. All right. So describe what movements could be done with patty paper. With patty paper copy of quadrilateral, so that the original one, make original orange. Original is going to be orange. So it lays on top of prime. Okay, well, it looks like looks like it's going to be a clock. It's going to be a counterclockwise rotation. So you know what? I wouldn't even need to do this with patty paper. Right? If I have an L and I map it to L prime. Okay, that's 90-degree angle right there. All right, so that's a 90-degree angle. I wonder if it is a rotation. So let me just grab 2 points that are corresponding. I'm gonna grab T, and that is T is 1 and -5, and T prime is 5 and -1, and I will say that my x coordinate in terms of my prime coordinates in terms of my non-prime values are, let's see, my x and my y is flopped, and my, oh wait a minute, x is not negative, hold on. T was 5 comma comma t prime was 5 comma 1, not negative 1. 5 comma 1. And so then it looks like my x value turned that. So it looks like that was a counterclockwise rotation. Wait a minute, hold on a second. Hold on just a second. It's a clockwise rotation. Something went wrong here. Okay, so t is negative 1 is 1 comma negative 5. Is that what I had before? I don't remember. T prime was 5 comma 1. Okay, so my prime values in terms of my y values are y, or my y's and my x's flopped. Oh, my y changed. Yeah, so my y changed. That's right. Okay, so my y value was my y value became swapped. That's where I made my mistake. Yeah, so this is so my coordinate expression is x comma y. Well, technically, I guess if I'm going to color code it right, it's going to be x comma y pulls from negative y comma x, and that's going to be a counterclockwise rotation. So that's a counterclockwise rotation. And you can do that with patty paper too. And just be like, hey, here's my thing. Put this here, and it's a 90-degree rotation. 90 degrees. 90 degrees. Okay, so then, so 90-degree counterclockwise rotation. Describe the movements that you've done with patty paper, quadrado, so that we'll do our green. Green lays on top of, this is going to be a blue one, I'll make this blue, lays on top of double prime. This is going to be a reflection across the x-axis, so it's going to be to fold it on the dotted line. You'll see if I fold it on the dotted line or flip it, it's going to be my thing. And so this is a reflection. This is going to be reflect over. Move that up over. Reflect over this line here. X equals y, because every change, one change for x, I have a one change for y. Okay, so this is a reflect over the line x equals y, and then that algebraic expression equal is this negative y comma x. No, that's not right. Is x is y comma x, is y comma x. That's a much faster way to do that if you memorize your stuff. I could pull like w's off it and w prime, right? And say I guess if you don't make a mistake, so I could do that. All right, so let me go ahead and prove it with my thing here. Let me go ahead and pull w. W is or w prime is 4 comma 2 comma 2, and w double prime. W prime is 2 comma 4. 2 comma 4, and it's pretty easy to see. that it was my w in terms of my x and y, but my original term was y comma x. This is my y term, this was my x term. So pretty easy. All right. Okay, so the next one is complete the statements here. So the transformation sequence are both examples of isometric transformations, right? Because all of them can be mapped of the original point. Okay, and then use the definition of congruence. Oh, you can't see that. Use the definition of congruence in terms of rigid motions to explain how both sequences of transformations of quadrilateral, the one we talked about, resulted in this, the original one, being congruent to the double ones. Okay, well, rigid transformations result in congruent figures. So that's that, right? So congruent terms, yeah. So that's all you really got to say is rigid transformation. All the transformations that we did were rigid transformations, and rigid transformations preserve distance and result in congruent figures. That's what I'd say. So that's it. That is section 4.6.